mitigation by capacity building for earthquake disaster. Okay, now if you take a past history of a disaster in our country, so there are so many disasters like earthquake, tsunami, cyclone, okay, landslide, and the flood is sort of natural disaster, and they are also man-made disaster also. To some extent, a man-made disaster also. So during all this disaster, we witness almost so many loss of people. Okay, so even then we could not mitigate the risk involved in this particular, especially in the earthquake disaster. So the reason began is lack of capacity building, and increasing the vulnerability. Okay, so now this short-term STP is aiming for risk mitigation actually, risk mitigation during the disaster. So before getting to this topic, I would like to introduce this word hazard and a disaster. What is the difference between the hazard and disaster? Okay, so if I recently if I happen to see, there are a number of disasters like tsunami, cyclone, landslide, flood. Okay, so these are all called hazard actually, hazard. But when we look at the, suppose if you look at this hill, there is a hill here. The stone is expected to fall over this person. The person standing underneath the hill. Okay, the falling of the stone is termed as hazard, and it cannot be stopped. Likewise, the earthquake, tsunami, cyclone, they are called as hazard, and it cannot be stopped because it's a natural phenomenon. Okay. Now, only one person is standing here. He is expected to lose his life. When the hazard turns to disaster, only it becomes a disaster. Okay, the hazard turns to disaster only if you lose the people. So now, can you imagine the earthquake happens at Chennai? The same with the magnitude of a 6 or a 60 Richter scale. The same earthquake happens at the Rajasthan desert area. So, what will be the difference between these two hazards? Anyone? Earthquake happens at the Chennai and the Rajasthan. See, with the same magnitude. So, what is the difference you can observe here? With the suppose magnitude of 6, suppose let us assume that 6.0. So in Chennai, it is a very crowded place, but in case of Rajasthan desert area, so it won't be any crowded. So what is the main difference is we are expected to lose more number of people at Chennai. So in Chennai, it is called as a disaster. Okay, in Rajasthan, it is called as a hazard. The same earthquake with the magnitude of 6. Okay, happens at Chennai and Rajasthan is named in two different names. One is hazard and another one is disaster. Okay, so now it becomes a disaster now. So the our government of India now, okay, is taken over. Earlier it was the agriculture ministry was giving the relief measures only after disaster. Now the MHA is taken over. The purpose of MHA in disaster mitigation is they are concentrating only number one is mitigating measures, number two preparedness. Okay, they are pumping a lot of money in preparedness actually. So we suppose the same scenario if we take the stone is expected to fall over the hill. Okay, this person. Now if he is under the shelter, he is not expected to lose the life of the people. So these are all called mitigation measures. And at the same time, somebody can alert him so that he can escape. So his life will be saved. So they are called as a preparedness. So nowadays, government of India is spending more money on this mitigation and proper preparedness. Okay, so is the case for this say HTTP program. Okay? In case if you see the relationships, so what will be risk here? Risk is hazard multiplied by vulnerability actually. Hazard multiplied by vulnerability is going to be the risk, okay, minus capacity. Now, suppose if we name some number for the falling of the stone from the hill, like let us name it as 10, only one person is standing here, so the risk will be 10 actually. The risk will be 10. Now, to minimize the risk to 0, so what needs to be done? Anyone can suggest now. I want to have the risk to be zero. What should I do? Anyone can respond now.
Capacity also should be 10.
Yes, we can increase the capacity or we can reduce the vulnerability to zero. So in both cases, it is possible to minimize the risk, isn't it? So in this workshop aims to increase the capacity so that the risk is minimized to zero. So that is what the idea behind this. So we are focusing only in the natural disaster like earthquake. So in case of earthquake, we want to minimize the risk to zero so that there is no life loss. To decrease the life loss, to decrease the risk, we need to increase the capacity enhancement in the society. Number one. Number two, you have to reduce the vulnerability to some extent so that the risk also minimizes zero. So this both way it is possible to minimize the risk. Now we are aiming for increasing the capacity so that the risk is made to zero now. So that is what our objective of this workshop. So when we say hazard, as I told, the natural hazard, it can be a landslide, it can be a earthquake, it can be flood, cyclone, tsunami, whatever may be, but it cannot be prevented. It is a natural phenomenon that is threat to the humans. Okay, and the vulnerability is exposure to loss of life. More number of people. How many number of people are expected to lose the life? So that's what we refer vulnerability here, and the capacity. So how to meet out this hazard with available resources like men and material with the potential resources. That's what our capacity. So we need to increase the capacity, reduce the vulnerability, so that the risk can become zero. Okay. So our objective is to bring the risk to bare minimum by increasing the capacity or by reducing the vulnerability. Okay. So that is what our aim of this actually particular program now. Okay. So if you look at this disaster management chart here, so this is what the incident occurred, maybe earthquake or tsunami or cyclone. So immediately our government of India tries to spend money on the response and the rehabilitation measures. So they will be giving a lot of money for the victims, and they will spend money on the reconstruction and rehabilitation measures. But after it, now the government of India is emphasizing more on the prevention, mitigation, and preparedness. That is what we say capacity development. Okay, so more money is spent on mitigation, preparedness, and the prevention. So that is why we have to create the awareness among the people so that the preparedness, if it is increased, so we can minimize the risk. Okay, and we can spend more money on the mitigation measures like earthquake resistant type of design or cyclone resistant of design or tsunami resistant type of design. So we have to go for resistant structures, resilient structures, and we have preventive measures. The guidelines can be given to the society or people so that we can minimize the risk. Okay, so these are all strategy we have to work out to minimize the risk here. So if we look at this animation, that is a 2004 tsunami earthquake that happens at Sumatra. Happened at Sumatra. So the waves which are originated at the Sumatra, it has reached our seashore almost 5 hours duration. After 5 hours only, we reached these waves. Okay, the waves reached the eastern coast of India after just 5 hours of this initiation of the waves propagation. Okay, so this 5 hours is more than sufficient to vacate the peoples all along the seashore. So we failed to do it. So suppose if you are taken the waves, photo of that waves at that particular location. So what is the amplitude and the frequency of the wave? If you know that amplitude and frequency of the wave, it is possible to calculate how far this rays will reach. Okay, what is the intensity the particular wave is carrying? How much energy is carried by this wave, and how far it can reach. So even then we could not save the people because of the lack of preparedness, awareness. So that is why the government of India is spending more on creating awareness. Nowadays we have floating bodies everywhere in the Indian Ocean, so that will give the indication about the tsunami now. Okay, so that is what the importance of the preparedness now. Okay, so the seismic risk It directly depends upon the hazard and vulnerability here. If you happen to see this, the seismic is directly depends upon the hazard and vulnerability, or the exposure of the element at the risk. So it can be minimized if you reduce the vulnerability. Okay, if it is put to a small circle, then the vulnerability will be risk will be reduced. In case the vulnerability is reduced, risk is also reduced. We cannot have control over the hazard. Okay, so that is what the objective now. So we look at this table. So that global occurrence of the earthquake. Okay, so more than 8 Richter scale, almost only one number. Okay, is one number of only one number is expected to happen throughout the world. That is more than 8. So between 7 to 8, almost 80 numbers of earthquakes are expected to happen. Between 6 to 7, it's almost 120. We happen to see the energy released during each earthquake. Okay, this is given this particular column. So if you happen to compare, so the 199,000 divided by 6270, it is going to be approximately 30. Same way 6270 divided by 199 is approximately 30. So that means increasing one number in the Richter scale results almost 30 times damage. Can you imagine now? So the damage, extent of damage will be almost 30 times because the energy release is almost 30 times. So we cannot say it is only one number increase in the Richter scale magnitude. So now also the earthquakes happening, the shaking of the ground is happening. Only thing we are not able to perceive. Okay, it is less than 3 now. Okay, approximately. So this one more table. If you look at this table, uh, so only one down south of Tamil Nadu we have Coimbatore here. That is 1900. So that is earthquake with the magnitude of 6. And reported death is almost nil. Okay. Rest of the area, if you happen to see, these are all Assam, Gangra, Nepal, Assam again, Anjar, Bihar, Nepal, Uttarkasi, Kildari, and Chamoli. That is up to 2001 record. Okay, so what actually it indicates why only these northeast segments of the areas are affected by earthquake? Anyone? Can you give any hints? Yes. So Assam, Bihar, again Assam, Anjar, Nepal, Uttarkasi, Killari. So these are all the region of northeast. Why earthquakes are frequently happening in that regions?
Sir, might be because of tectonic plates movement.
Very good, very good. So we will. I will let you know about the tectonic plates. What is that actually? Okay, maybe it is correct actually because of the tectonic plates. Yeah, what we understand from that, we will see that. Okay, exactly correct. We have the two plates, Indo-Australian plate, Eurasian plate, that is expected to collide at Himalaya belt, okay, northeastern center. It's very correct. So these are all the content I wanted to discuss with you. So number one, what are the causes of earthquake? So if you happen to see earthquake, okay, before that, so you have two water tanks kept at the same level. Okay, so the tanks are filled with the water. Now, if I'm connecting a pipeline in between, the water is expected to flow. Okay, now is there any water flows in the pipeline? Both are having filled water. Is there any flow of the water in the pipeline? Because if the water is filled in both the tank, okay, will there be any flow of water in the pipeline?
No, there won't be any
No, sir.
flow.
Okay, no. So if the same water tank is kept at a different level, now the water flows from higher level to lower level. Yes, do you agree or not?
Yes.
Yes, sir.
Okay. So the flow of water took place because of the difference in the head. Same if you take a piece of wire. So if I'm giving a potential here, 100 volt, 10 volt, suppose. Here only, here also 10 voltage. Will there be any flow of current in the wire?
No, sir. If the voltage will
No,
remain
because the
same, no
potential
problem.
difference is 0. 10 minus 10, it is 0. Suppose instead of a 10, if I'm going for 100 now, 100 minus 10 now. Now the potential difference will be 90. So the current is expected to flow in the piece of wire. Is it clear? So when the voltage increases, potential difference increases, current flow takes place. Same way here, the head is increases, the water flows. Same way, during formation of earth, what happened is the high density particle got deposited at the core. That is we call as a core. High density and high density particle got deposited at the core. Lightweight particle rose to the surface. That we call as a crust. Okay. Now, if you compare the pressure, temperature, density between the core and the crust, the pressure will be maximum at the core, I suppose. Will you agree with me? And temperature also will be maximum at the core. And density also will be maximum. Here it will be less. Because of the difference in the pressure between the core and the crust, because of the difference in temperature between the core and crust, because of the density difference between the core and crust, there current flow. There is a formation of current which flows in the mantle region, in between region. Okay, so that current makes this mantle to move. So that means mantle is semi-solid. It is in nature keeps on moving actually. Okay, so this is what I was telling about. So we have the core and the crust. We have a crust here. Core is here. So at the core we have the temperature 2500 degrees centigrade, but at the surface it is only 25 degrees centigrade. Okay, so maximum 40 degrees centigrade. Same way, the pressure at the core will be almost 4 million atmospheres, but at the surface it is going to be only 1 atmosphere, 1 kg per centimeter square. Same with the density, it is going to be 13.5 gram per cc. Here it is going to be only 1.5 gram per cc. So because of the difference in temperature, pressure, density between the core and crust, there forms a current. So this is what we call as a convection current. Okay. So the convection current makes this mantle to move. So the mantle keeps on moving. Okay, it is like egg. We can visualize like egg. Okay. So the inner core, it's yellow portion. So this white portion is the mantle. Suppose let us assume that. Okay, this is what we say. It is suppose crest. We can resemble crest. Likewise, but the skull is made up of a number of patches. Okay, like our human skull, it is like a patches. Same way, the earth also we have 7 major plates which are floating over the mantle material. So we have like plates are floating in the mantle. Okay, so when the plates are floating in the mantle, what is happening is it is expected to make a collision. Okay, so the plates are moving because the mantle is moving. The mantle is moving because the current is developed. The current is developed because of the potential difference, temperature difference, pressure difference, density difference between the core and crust. Is it okay now? How come the plates are moving? The plates are moving because the mantle underneath the plate also moving. The mantle is moving because of the current developed. The current is developed because of the differential temperature, pressure, and the density between the core and crust. Is it okay? So in this process, what is going to happen is the plates are expected to come closer to each other and make a collision. So these are all area of vulnerability. So here earthquakes are expected to happen every time. So all along the plate boundary, we can suspect the earthquake. Okay, so in those area, it is mandatory that we have to go for design of earthquake resistant structures. Is it okay? I suppose it's clear about tectonic plates. So during the formation of earth itself, what happened is the heavier particle got deposited in the center that we call as a core. The lightweight particle rose to the surface, so that we call as a crust. So what is happening is the crust is having the patches like 7 major plates. Okay, they are floating in the mantle. The mantle is moving because of the current is developed. The current is developed because of the temperature, pressure difference, density difference between the core and the crust. Okay, so that's what we say. It's a plate tectonics. So this is what the plates: Eurasian plate, Indo-Australian plate, Pacific plate, North American plate, South American plate, and African plate. Here, if you happen to see this portion, this is our India. So India is in the Indo-Australian plate. Okay. So here what happened is the Indo-Asian plate and the Eurasian plates are expected to collide at this particular region. So that is why the formation of Himalaya. So the Indo-Asian plate and the Eurasian plate, so it is moved one over another. So that results in the creation of the Himalaya. Okay. The Himalaya formation took place because of the movement of the Indo-Asian plate and the Eurasian plate. Okay, it is told that all major seven plates are moving, keeps on moving at 1 centimeter to 13 centimeter per year. Okay, so that the Indo-Asian plate moves close to Eurasian plate. So that is why the Himalaya formation took place. So now also these vibrations are happening at this particular region. So that is the reason for the table which I shown earlier. The northeast regions are vulnerable to earthquake because of the plate tectonics. Okay. So this is what happens actually. So when the plates are moving close to each other, we call it as a convergent boundary. So the hill formation is expected to develop now. When the plates are moving away from each other, that is called a divergent boundary. So here we are expected to develop a valley formation. Okay? So this is called the transform boundary. So sharing action. Okay? So these plates are expected to move only until these three conditions. Okay? So this is number one reason. That is plate tectonic theory. Number two, any disturbance happening underneath the earth crust. Okay, that is also is possible. That is one more reason. Suppose if you have a number of layers of rock, okay, we have the granite here limestone. Likewise, we have a number of layers of rock. So each layers of rock will have a different elastic modulus. Okay. Suppose if you have a building constructed over this particular region, it is very confined. Okay, in this case, what happens is the load versus deformation. If you plot the graph, load versus deformation graph. Okay, this is entire load. Suppose this is weak rock, that is the limestone. Okay, these are granite. So heavy weight particles. Okay, so these are entire. That's what we can plot into the y-axis P, and this elastic modulus of this particular rock layer is very less. So that we call as a limestone. Suppose let us take. So in this case, it is going to be vulnerable. So this limestone rock is expected to get broken. Okay. So in that case, what happened all along the fault, it is going to have this slide. So that movement of the rock, okay, that particular layer. So that is what we call as a focus. Okay. Suppose the rupture of rock takes place. So underneath the earth crust at a weaker level portion is called as a focus point, the point where the rupture of rock takes place. Now, in case if you plot P versus delta, that is a rupture of rock. Before rupture of rock, the plates are expected to move. That is delta here. So the area under the graph multiplied by the volume of the material just above the focus point will give the amount of energy released during earthquake. Okay, the amount of energy released during earthquake is the area under the graph multiplied by volume of the material just above the focus point. So that much amount of energy is expected to release during earthquake at the focus point. So releasing what happens is the waves are created. See, any vibration happens underneath the earth crust. Okay, causes a wave propagation, initiation of the wave. Okay, that wave only we call it as a body waves. That is primary wave and the secondary wave. So when the waves reaches the crust at the surface, okay, when it propagates underneath the structure, it is expected to move the structure in to and fro motion and up and down motion. Make the structures to move to and fro and up and down motion. So that's the problem comes here. Okay. So this is a second reason. Any rupture takes place underneath the earth crust is also a reason for the earthquake. Okay. Number one is a plate tectonic. Number two is any disturbance happens underneath the earth crust is also a reason for the earthquake. So the rupture takes place at the point where we call it as a focus. And the waves, when it comes out of the surface, just above the focus point at the epicenter. Okay, that point we call as epicenter. Is it clear now? So far we discussed about only two things. Number one is a causes of earthquake. In the cause of earthquake, there are two reasons. Number one is movement of the plates, tectonic plates. Number two, rupture of rock underneath the earth crust. Okay, so what happens is when the rupture of rock takes place, the waves are initiated. Okay, any vibration happens in a solid medium induces a wave. Okay, any vibration happens in the solid medium induces a wave. Okay, when the waves comes out of the surface at the epicenter, the surface waves are generated. Okay, these waves which are originated at a focus point is we call as the body waves. Body waves, that is primary wave and secondary wave. So when the primary wave and the secondary wave propagates underneath your structure, it's not expected to damage the structure fully. But when the structures, when the primary wave comes out of the surface at the epicenter, it makes the structures to move in a to and from motion, up and down motion. That wave we call as a surface wave. The surface waves are more dangerous than that of body waves. So, so we will see how to tackle these waves so that we can avoid the, because earthquake doesn't kill the people. Earthquake doesn't kill the people. Only the poor built structures are responsible for killing the people. So you and me are responsible. Now we should be able to safeguard the structure so that we can safeguard the people. So by suitable design of the structure. Okay. So this what happens in the seismograph when the waves are arriving. So the first disturbance in the seismograph we can witness this is arrival of that indicates arrival of P waves. The second disturbance indicates arrival of S waves. Okay. So from that it is possible to calculate the magnitude of earthquake. You will see that. Okay. So this is what the focus point where the rupture of took place. Okay. This is what we mean the delta here. So the P versus delta when we plot the graph. So the area on the curve multiplied by volume of the material just above the focus point will give the amount of energy released during earthquake. Okay, that energy only we say in the number like Richter scale magnitude. Okay, so we can visualize this actually the delta and the surface also. Sometimes it is not every time you can see that. Okay, so if you happen to see this graph, this two objects, here we have the balloon, here we have the lorry tire. Okay, we are filling the balloon with some amount of air pressure. The same amount of air pressures are filled with the lorry tire also. So when the bursting takes place, which is expected to make a louder noise? Can anyone suggest? Both are filled with the same amount of air pressure. The balloon and the lorry tire. When the bursting takes place, which is expected to make louder noise?
Tire, obviously.
Tire. Why? Why tire?
It can hold the more amount of pressure rather than the balloon.
Okay. It can hold only more amount of pressure. But here my condition is I am applying equal amount of air pressure.
Then it will be, sir, balloon only.
But obviously we could hear louder noise in case of lorry when it is bursting of the tire takes place, isn't it?
But the balloon can't hold the same pressure as of the tire. So in this case, first the balloon will get uh, burst rather than the tire because it can have a thick walls which it
Okay.
can hold more amount rather than that of balloons.
Balloon. Okay. So another interpretation. So if you happen to see here balloon, we can plot the graph load versus deformation for both the balloon and the graph. So in case if we plot, it will be like this. Okay, it is going to deform more. But in the same graph, in case of tire, it will be like this. Okay, in case if we calculate the area under the curve for both cases, multiply by volume of the material, that is the balloon here, here lorry tire, which will have the more energy. area under the curve multiplied by volume of the balloon. Volume of the balloon means the thickness and multiplied by surface, we can say, surface area. The same way here, the volume will be more for tire. And the area under the curve will be maybe less or more, okay, than that of balloon. But the volume is, it is going to be more. So that means the energy absorbed in the tire will be more than that of balloon. Do you agree or not? The energy absorbed, how much amount of energy is absorbed, that is going to be released in the form of sound energy. So that is why the tire when it bursts, it makes louder noise. Same way, is it clear?
Yes, sir.
Same way, in case the rupture of rock takes place underneath the earth crust, somewhere here. Okay. So this much amount of energy are expected to release. If in case if you are plotting load versus deformation, okay, the graph, area under the graph multiplied by volume of the material just above the focus point is going to be released. So that amount of energy only we say it's electric magnitude of earthquake. Okay. So these are all the layers of rock underneath the earth crust. So many layers. I suppose we got the answer for this. So what are the causes of earthquake? Number one is movement of the tectonic plates. Number two is any disturbance happens underneath the earth crust. Okay. So this is what a brief introduction to cause of earthquake. So when the earthquake happens, what happens is these waves are expected to create. These waves we call it as primary waves. That is originated at the focus point. So even soil particles are expected to move in to and from motion. So it moves in forward direction, comes back to occupy its original position. Just to observe the particle. Comes back to occupy its original position. So this is how our buildings are so expected to happen in building also. The movement will be in forward direction, comes back to occupy its original position. This we call as the primary wave. That is originated at a focus point. So the one more wave, okay, this is what the primary wave. We look at the black dot. So this is what happens in the soil. It is getting compressed and elongated. In case if you look at the soil sample at a particular location, the soil samples are expected to get compressed and it gets elongated. This is what going to be in the building also. Okay, this is what regarding the primary waves. So this is what about this wave? This is secondary wave, S waves, shear wave. That is also originated at a focus point. So just after primary wave, the secondary waves are expected to happen. Okay. So this is going to be in case if you tie a rope in a wall, just to give a jerk. So the wave propagation. So that means each and every particle will be vibrating in vertical plane. So that is what the S wave propagation. So this is what we call as a body wave. So imagine these waves are when it propagates underneath your building, the building is expected to move up and down motion. Okay. Can you see now?
Yes, sir. Yes, sir.
Okay. So this is what which wave actually this one? Is it a primary wave or S wave?
Yes, right, sir.
S wave. So if you draw a line here, the each and every particle will be vibrating its own plane. It is not going to divert from its original plane. If you take any line, all the particles are vibrating in the same plane. So that's what the main phenomenon of S wave. Actually, when the S wave propagates, each and every particle will be vibrating in vertical plane. So the our building also is expected to move upward, up and down motion. So when the building goes upward, there is no problem because we have given factor of safety. Okay, so building is safe actually, up and down motion. But when the building is moving to and from motion, that's where the problem comes. Okay, so just imagine the S wave propagation in the soil sample. So one of the diagonal is getting increased, other diagonal is getting compressed. Okay, that is what is shear wave propagation. Now the both primary wave and the secondary wave, they are expected to originate at the focus point here. Primary wave and the secondary wave. First primary wave will travel faster than that of secondary wave. Okay, the both waves are originating at the focus point. When the both wave comes out of the surface at the epicenter, okay, at the surface waves are generated. Okay, so that when it propagates underneath the structure makes the problem. Actually. So this is what the surface waves. We call it as a Rayleigh wave. Just look at the dot. So it is just in the moving in the form of elliptical fashion. Your building also is going to be moved in the elliptical fashion when the surface waves are propagating. So this is what the problem is. When it is moving up and down, there won't be much problem. When the building is expected to move in the sea waves, elliptical fashion, there the problem comes. So that is why the surface waves are more dangerous. So that happens only at the epicenter. At the epicenter, when the waves are initiated, the surface waves are generated. These surface waves are number one is the Rayleigh waves, number two is the love waves. So the both waves are expected to originate at the epicenter. So the love wave is nothing but the S wave. Okay, but it in the original plane actually. It is like a snake movement. Okay? So these love waves and the Rayleigh waves are more dangerous than that of primary waves and the secondary waves. So we should be able to tackle these love waves and the Rayleigh waves to safeguard the structure. Okay. Now look at this picture. Okay, these are all the buildings completely collapsed. Okay, but these buildings are okay. This building also okay. So what may be the reason? It is in the same soil. Okay, why these buildings are okay? Why these buildings got collapsed?
Frequency reduced from the sensor.
Yes,
Frequency of energy will be reduced.
frequency. Okay, any other reason? So these buildings are okay. So this is very important actually point we have to learn actually. So suppose let us take this is our map here. We are at the Chennai. Okay, at Chennai here. Okay, some epicenter is available at like let us take in Chennai and Coimbatore also. So this is a epicenter. This is what the location of the building. So if you orient the building in this direction, the building will be safe. If you orient the building in this way, it is going to be dangerous. Why? So this is what the epicenter location. You are orient the building in this direction. It's okay. When we orient the building in this direction, perpendicular to the wave propagation, it is going to be very dangerous. Why? Suppose if you look at this rectangle, okay, so this is D, this will be B. So the moment of inertia of this portion will be B d cube divided by 12, D cube. So B D cube. Okay, the D will be the parallel to the wave propagation. Okay, so wherever the dimension, suppose if the force and the dimension, if it is parallel, so that will be a D actually. D moment of inertia. If we calculate the moment of inertia for this rectangle building. Same way, if we calculate the moment of inertia for this building, this will become a D, this will become a B here. So moment of inertia will be less here. Here moment of inertia will be more here. Moment of inertia is directly proportional to K. That is stiffness of the building. So here the stiffness is more, K is more here. Here K is less here. Is it clear now? So that means you have to orient the building in the direction of the wave propagation. So for that you have to look at the wave epicenter. Where the epicenter is there? where you are going to construct your building. So if you both points, if you know if this known to you now you can orient the building in this direction. That is number one point actually. So we can safeguard the building from the earthquake collapse. So the orientation of the building matter actually. So these are all the buildings, same type of building only, but these buildings are safe because of this orientation. The wave propagation had taken place in this direction. Is it clear now? Shall I go to the next point? Okay.
Yes, sir.
Okay. Now, so far we have seen the causes and the waves and the orientation of the building. Okay. So measurement of earthquake, I will not go get into the details. So there are two measurements. One is a quantitative measurement, and another one is qualitative measurement. Okay. So that we call it a magnitude. Here we call it intensity. Okay. So in case of a cube, if we happen to see a cube, a M30 grade of concrete, M30, that indicates okay 30 Newton per mm square. So that we say it is in the quantity magnitude. So if we say in quality, it is a good concrete, a poor concrete, moderate concrete. So that's why we call it a qualitative measurement. Same earthquake also we say in number because it's in the magnitude. Okay, we say it's a magnitude. Energy released during earthquake is termed in the form of number. So that we say it's magnitude. Quantitatively, if we measure the earthquake by merely observing the extent of damage, that we call intensity. Okay, so good, bad, or worst by merely based on the observation. Okay, suppose there is a huge crack in the wall, there is a huge crack in the beam, there is a huge crack in the column. So merely based on the observation, if we classify the earthquake, that we say its intensity. Okay, so magnitude it can be calculated by using a Richter, that is by using seismogram. Okay, we will see that how that earthquakes are expected to. Actually, I want to discuss so many things, but the time is not there. Go fast. So this is what we say. It's a Richter scale. So as and when the earthquake comes, suppose let us take a earthquake happens at Delhi. So I am measuring at Chennai here. Okay. So this is what the waveform I got. Now in the initial primary waves is the initiation of the that the arrival of the primary wave. First arrival of the primary wave. After some time the secondary waves arrived. So the amplitude is getting increased. So after sometimes the relay waves and the love waves will come. Okay. Now this is arrival of the primary wave. Here the arrival of the secondary wave. So the primary wave and secondary wave, the time difference is noted here. That is 24 seconds. That is marked in the first scale, 24 seconds. We have three scales marked with the number. The first scale I am marking the SP difference, primary wave and the secondary wave difference time. And the third scale I am marking the amplitude of the secondary wave. That is 23 mm. Okay. So when I'm joining these 2 points, it is going to cut at this particular intersection. It is going to intersect at the central scale. That scale we refer as a Richter scale. So it is expecting to intersect the number 5 now. That means the Richter scale magnitude 5. Okay. So this is how we measure the earthquake magnitude in Richter scale. Suppose if you are measuring the same earthquake in Japan, from Japan, what happened? The SP time difference will be somewhere here. Okay, the amplitude of the second wave will be somewhere here, but the magnitude is not going to change. It is going to pass the same magnitude, 5. So that is why it is universally accepted, Richter scale magnitude. Is it clear now? So that the number indicates amount of energy released during earthquake. Okay. So this is what a seismograph. We are recording the information about the that is in the paper. That paper is called seismogram. Okay. 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 These are classification of the earthquake. We will not get into this. Now the important topic: load path. Okay. So we know that in a building, the load is getting transferred through the elements of the building. That is, from slab to beam, beam to column, column to the foundation, foundation to soil. Okay. So in case if you are able to transfer the load, so in case this is the building, okay, from the slab, it goes to the beam. From beam, it is go to the column. From column, it goes to the foundation. Foundation goes to the soil. So that is what the load path conventionally we design actually. Okay. So whatever the loads are available, let us take 100 unit of load at the top. Okay. The soil also will have to have the same 100 unit of load. The load transfer should happen actually. No element in the building should withstand the load. Whether it is a beam or a slab or a column, should not take the load. So it should transfer the load to the other element. So from slab to beam, beam to column, column to the foundation, foundation to the soil. So our design should be just that whatever the external loads are available, that needs to be transferred to the soil without any dissipation. So that is what our objective of the design actually. Okay. But here problem comes. Here there is a problem. What is the problem? We will see that. So in case of load path, what happens is, let us imagine. Okay. So when the wave propagates under the structure, when the wave propagates under the structure, the building is expected to move in up and down motion and to and from motion also. Okay. So it is both way it is possible. Building is expected to move up and down and to and from motion. Up and down and to and from motion. So when the up and down it moves, okay, the damage is occurring, but it's not going to be very much damage. But when the buildings are moving to and from motion, okay, we are going to have the a force called inertia force, which is expected to act urgently. Okay, so let us imagine here there is a building here. Okay, when the wave propagates under the structure, okay, your foundation which is connected to the soil is also goes in the direction of the wave, but your upper story is not going to cooperate with your foundation. It is going to experience a force in opposite direction. Let us assume that I am standing in the bus. I am standing in the bus. Okay, so all of a sudden driver starts the bus. My feet, which is touching the floor of the bus, goes along with the bus, but my upper body is going to experience a force in opposite direction. This, this is what the bus moves in forward direction. I am standing in the bus. My upper body is going to experience a force in opposite direction. That force depends upon the mass of my body. Okay, the acceleration of the bus structure. So this force, mass multiplied by acceleration is a force, which is going to push me downward. Okay, then now just replace me with the building. I am standing in the bus. My feet, which is touching the floor of the bus, goes along with the bus. Okay, but my upper body is going to experience a force in opposite direction. That force will be mass times acceleration. If I have more mass at the upper body, I am going to receive more amount of force. If I am having less mass at the upper body, I am going to receive less amount of force. The same thing happens in the building also. That pushes the building in opposite direction. Okay, now that is a problem. Now this force I have not taken in my design. I have taken only live load and dead load for design purpose. Okay, for drawing this here force and the building. But here is the case. There is a force which pushes me horizontally. That the force is not being taken in our design at all. How can we say how can you say earthquake destroy the building? So that means if we are able to take these forces also in your design, now we can say that the building can be safe. Okay, you are not taking this force. Not only that, so the force which are available at the roof level that cannot be transferred to the soil without any depreciation. Suppose the same 100 unit of force is available at the roof level cannot go as a 100 here at the soil also. Unlike in case of live load, dead load. So that is what the main reason for the collapse of the building. So whatever the force are generated at the roof level, that has to be transferred to the soil without any distribution. So we will see what are the potential deficiency exist in our society in buildings. Number one is we don't consider the information regarding the inertia force in our design. Okay. So this is what happens when the ground waves propagates under the structure. Okay, the foundation moves, but your upper story is going to experience a force in opposite direction. So that force, okay, is not being able to transfer to the soil. So this is a force. That is 100 unit of force at the roof level. So that is inertia force. Where frictional forces should be such that the same amount of 100 unit of force should be available here. So here 50, here should be 50. In such cases, it is possible to transfer the load. So you have to just go for these frictional forces. Okay, that should be equal to the developed process. Then it is possible. So this force can be transferred through the shear wall also. So we can provide a RC wall. So via this wall, it is possible to provide we can transfer the load, external force. So both ways it is possible. Okay, horizontal force. So these are the provision. We can transfer the number one is moment resisting frame, ordinary moment resisting frame. This is braced frame wall that is with the shear wall. So like this provision, it is possible to transfer the horizontal force. Okay. So, so the transfer load path is very important. So whatever the force are expected to generate at the roof level, that has to be transferred to the soil without any dissipation. So in case if you are able to do it, building will be safe. Okay. So that is what regarding the load path. In case if you look at the soft story and the weak story, two story failures, in case of earthquake resistant type of building. So what you will see, what is that soft story, weak story, you will see that. Okay. So this is our conventional building in urban area. Okay, we have the car parking at the ground floor. So we construct the building in such a way that all the we give open story at the ground floor. We construct for our convenience. So what happens is when we have the building, okay, so this earthquake force are expected to act at each and every floor. So that is horizontally acting. It is acting horizontally. It is like a cantilever beam with inverter cantilever beam with a number of point load. So if you draw a shear force diagram for this beam, suppose let us take 2, 3, 5. So how can you draw the shear force diagram? It will be 2, so it will be 5, it will be 5 plus 5, 10. So this is what shear force diagram for this cantilever beam. So here also this a case of inverted cantilever. The building is fixed at the bottom here. The force are expected to act horizontally. So the building is moving as like inverted cantilever. The shear is expected to get accumulated at the bottom. The shear accumulation is expected to happen at the bottom. So more shear accumulations are expected at the bottom. Okay. So, but we don't have any shear resistance at the bottom. So more shear is expected to develop at the ground floor, but we have there is no resistance to shear at the bottom. So that is why the building is expected to get sheared off at the ground floor. The building will be falling down. Okay. So we should avoid the open ground story. So before that, so what is that actually shear force here? Can anyone say what it would be shear force? So what is that shear which is expected to damage at the ground floor? What is it actually shear? So suppose if you look at the broomstick, okay. So I am cutting the broomstick with the scissor. Okay. So I'm giving a condition. You have to apply equal and opposite forces. Here also 5 Newton. Here also 5 Newton. Now, is it possible to cut this broomstick? Yes or no? Yes. Can you hear me?
Yes, sir.
Okay. Okay. Now, it is not possible to cut the broomstick because forces are equal and opposite. But by virtue of geometry of scissor, purposely it has been designed in such a way that it produces unequal forces, like a 15 Newton from the bottom, 5 Newton from the top. Now, the resultant force is 10 Newton. The 10 Newton is nothing but a shear force. Is it clear now? That shear force,
Yes, sir.
that unbalanced force at a section, we call it shear force. That shear is expected to accumulate at the bottom of this your building. This much is shear, unbalanced force. That is expected to shear of your ground floor car. So what you should do now? So we know how much is expected to see develop, how much amount of shear is expected to develop. So we have to increase the shear strength at the ground floor. Then it is possible to safeguard your building. Is it clear now? So that 10 Newton force here. Same with the accumulation of the shear, which is at the bottom is more. So that the shear is expected to shear of your ground floor column. So the building is expected to come down. So don't go for any open ground story for earthquake this type of. It is always suggested that the strength and the stiffness of the ground floor should be more. Okay. So just like see here, the accumulation of the shear is maximum at the ground floor, but one floor is missing here. It has gone down now because of lack of shear strength. So we have to avoid the open story, ground story. Okay. See, the shear is expected to be more at the ground floor. So that is why the maximum damage happens only at the ground floor. Is it clear now? Okay. So suppose if you have strength and stiffness uniformly distributed all over the building, then there won't be any problem. Okay. We have the luck and moreover, in case if you look at the historical building like a temple, churches, the strength and the stiffness will be more at the ground floor. Okay, so that means shear resistance is more. So that is why the historical buildings are not expected to collapse. So always we should not give any opening at the ground floor. Okay. Okay. So this is what the story demands, shear story, but the capacity should be more than that of story shear developed. So that is what the capacity enhancement. So your shear strength should be more than that of shear developed. So that is what the idea here. Okay. See, these buildings are expected to get collapsed because there is no shear resistance at all at the ground floor. We are given opening at the ground floor, and there is no resistance to shear at the ground floor. Stiffness is there is no stiffness at all compared to rest of the floor. So this stiffness irregularity, the failure because of the stiffness irregularity is called soft story failure. Okay, that we call as a soft story failure. Stiffness irregularity between the building should not be more than 20%. Stiffness irregularity should be avoided. Okay, that failure we call as a soft story failure. In case if you have lack of strength between the floors, that failure we call as a weak story failure. So that is what we have. Okay, so this building should be avoided. So always the failure is expected to the ground floor. Is it clear now?
Yes.
Okay. So we know about soft story and weak story. Irregularity in the stiffness is called as a soft story all along the height of the building. Irregularity in the strength all along the height of the building is called a weak story failure. Okay. Next, discontinuity in shear wall. Actually, we suggest that the shear wall should be provided to transfer the horizontal forces to the soil, which is developed at the roof level to the soil by using shear wall. But the problem is that when using the shear wall, sometimes it happens that we use the shear wall only at the upper story. We have no shear wall at the ground story and first story. That is very dangerous. Okay, so in case if you provide the shear wall, provide from the top to bottom of the building, up to ground level. Okay, So there should not be any discontinuity in the shear wall. Avoid discontinuous shear wall in a building. It's more dangerous. So the solution to the problem of the discontinuous shear wall is to eliminate the shear wall. Otherwise, don't provide any shear wall. Okay. Now next we go for suppose twisting of the building. So in case if you happen to see a building, symmetrical building, symmetrical or rectangular building, so we have the point called the center of gravity. Okay, CG, which is considered the center of the building. We have another point we call it center of rigidity. So center of gravity is a point where entire mass is expected to concentrate. Center of rigidity is a point where entire stiffness of the structure is expected to concentrate. Okay, so center of gravity and the center of stiffness. So in case if the center of gravity and the center of stiffness both are at a single point, the building will be safe. Okay, so if you take an unsymmetrical building, where we have the center of gravity here, center of rigidity is somewhere here. So in such cases, what is going to happen is the earthquake force which are expected to act at the center of gravity multiplied by the eccentricity between these 2 points will rotate the building in clockwise direction. There will be twisting in the building because the center of gravity point and the center of rigidity point is not at a single place. There is eccentricity between these 2 points, center of gravity and the center of rigidity. Okay, so between these 2 points there is a distance called eccentricity. Okay, that eccentricity is a reason for the rotation of the building, twisting of the building. So we have to make sure that the center of gravity and the center of rigidity should be at a single place in any building. Let it be symmetrical building or unsymmetrical. So for that, we have to move the center of rigidity towards this center of gravity point by closing the opening at this location, or giving the opening at this other end, so that we can move the center of rigidity towards center of gravity. So by doing that, we can avoid the rotation of the building, twisting of the building. Is it clear now? So for example, suppose, so there is a swing, a child is sitting over the swing, the length of the rope is same in both cases. If the child is sitting at the center of the swing, there is no problem at all. Center of gravity of the child and the center of rigidity of the swing, both are at a single place. The child is not expected to fall. When the child is sitting at the edge of the swing, the center of rigidity at center, there is eccentricity between these 2 points, which causes the rotation. So that is why the child falls. Is it okay? So the eccentricity is the reason for the failure of a building. The center of gravity point and the center of rigidity should be at a single place. Okay, suppose this is a rectangle building, we can say center of gravity and the center of rigidity at a single place. But what happened is during the usage of the building, we are using this building in this fashion. Suppose here we stored a heavy machinery here, one side of the building. So even though the building is symmetric, so during the usage, this side is going to be more load than that of this side. So the center of gravity is already shifted here. Okay, when the earthquake comes, the building is expected to fail, even though this building is symmetric in nature. The strength and stiffness is irregular all along the height of the building. Even though the strength and stiffness is okay, the center of gravity and the center of stiffness was okay. Now this building is expected to collapse because of the usage of the building. Okay, so that means it is not only the construction of the building and how to use this building during the over the period of time. That is also matter. Is it okay now? Why a building is getting twisted? Yes or no?
Yes, sir.
Okay. Suppose if you have unequal length of the column, unequal length of the rope, even though the Child sits at the center of the swing, she is expected to fall. Okay, it is a similar case here. In the sloping terrain, we have more number of columns. Okay, one of unequal length. Even the building is symmetric, the building is expected to get rotated or twisted because of the change in the center of gravity and the center of rigidity point at a different location. So for that, we have to go for correction. We will see that what we have to do. Okay. So this is ordinary table. Okay, where center of mass, center of gravity, and the center of rigidity at single place. Now I altered the table here. We have provided this type of a wooden portion here. This becomes unsymmetric now. Now the center of rigidity is somewhere here. Center of mass is somewhere here. Okay, so when I push the table, it is get rotated. It is getting rotated because of the eccentricity between these two points. Okay, so this concept is being used in a earthquake resistant building also. So you have to make sure that the center of gravity and the center of rigidity of a building should be at a single point. Okay, otherwise the building is expected to collapse. So we will see next the short column damage. What is the short column damage? If you happen to see in the sloping terrain, the building will have a different length of the column. Okay. So if you compare only two columns, only having the length of L, and another is L by 2 here. Okay, this is sloping terrain. Now when the earthquake forces are acting at each floor level, because of this force, this column is expected to deflect by delta. And the delta will remain same in both columns. Okay. Delta remains same in both columns. It is like a cantilever beam with the point at the free end. Okay. So the delta will be how much now? So it is a P. So this PL cube by 3A. Will be the delta. Okay. This delta. So the delta will be PL cube by 3A. Now in this case, if you happen to see the K, P is equal to K delta. So PP can cancel. K will be equal to 3A by L cube. That is stiffness of this column. 3A by L cube. So for same 3A by L cube, in case if we substitute the area of L is equal to L by 2, the column K will be 2A, 24A by L cube. So that means stiffness requirement for this column for the same moment of force is almost 8 times. So 24 by 3 is going to be 8. The stiffness requirement is going to be almost 8 times. So that means we need to increase the stiffness of the short column. That means moment of inertia of the column should be more. Short column moment of inertia should be more. But normally in case of sloping terrain, we have the same size of the column everywhere. So we are not going to change the size of the column. Okay, in case of a short column, we have to alter the size. So we have to increase the moment of inertia of the short column. Okay, so almost until the K becomes equal. So in such cases, it is possible to safeguard the building in case of sloping terrain. So if we are not increasing the moment of inertia, this column is expected to fail during earthquake. Short column is expected to get crushed. So that's what happens here. This short column will fail because it demands more stiffness. But the column size is not sufficient. So increase the column size so that stiffness will get increased. Okay. And the provision of the mezzanine floor in a building is also very dangerous. This building is suspected to act, this portion is suspected to act like a short column. Okay. So that is also very dangerous. So short column attracts more amount of earthquake forces. So what is the solution now? So this partial infill wall also is more dangerous. It is acting like a short column now. Okay. How? So this is what the short column. Okay, this is a long column now. When the forces are acting in this direction. Okay. So this length L, this L by 2. Let us imagine that. Okay, so the column stiffness is demands almost 24 EA by L cube. Here only 3 A by L cube. So almost 8 times more should be there. But here, because of the opening, the stiffness is very less by 8 times. So this column is expected to get damaged. So that's what we witness here. So it is acting like a short column here. It is fixed at this point. The length will be L by 2. So other here it is going to be L. Okay. So this short column is expected to get damaged. That is what we call it short column damage. So either you have to fill this infill panel with all along the height of the building. Yeah, or don't provide any infill panel. Partial infill should not be there. Okay, only glass panel or a fully covered infill panel. So partial infill should be avoided. Is it clear now? I suppose it's clear to you. Okay. So these are the failure of short columns. So what we can do is we can go for confinement of stirrups. So wherever it is suspected, suppose this is a short column. Here just to go for a closer spacing of the stirrups. So in this region. So that is what the solution here. So we'll have to go for confinement of stirrups all along the height of the building. Okay. So that is what the solution suggested. Is it clear now so far? Anything
Yes,
you
sir.
want to discuss? Okay, next we will go for a column beam joint. So the column beam joint is very much important because this area in this region is very small. Okay, smaller area, column beam joint. If you take a cube, okay, if we take a square portion, suppose. Now, when the earthquake forces are expected to act here, what happens is this square becomes rhombus. We agree or not? Yes or no? Okay, the square portion is expected to get distorted. It becomes rhombus. So that means this diagonal is getting increased. This diagonal is getting decreased. Okay. So the increasing diagonal is a reason for the failure. Suppose your concrete is weak in taking tension. So the X crack will be developed here. This crack will be developed all along the height, all along the joint here, diagonal joint. Okay, but here it's okay. This diagonal it's okay. Why? Because the concrete is starting taking compression, there won't be crack formation in this diagonal. But very next second, the force are reversed. So you are going to have X diagonal. This length of the diagonal is getting increased. So we are going to have the X diagonal crack here. So for only one cycle, just imagine number of cycles, n number of cycles. So that means the diagonal. Hello. Is it okay? It's clear?
Yes, sir.
Okay. I suppose it's the time is over, I suppose. Okay. Only 11 o'clock. Okay. Any doubt you want to discuss now? Okay. So far we discussed about what is the reason for earthquake and how do we measure earthquake by qualitative quantitative magnitude intensity. And we discussed about load path. We discussed about soft story and weak story and regarding shear wall, short column damage, twisting of the building, column intent. Okay. So so far we discussed about a potential deficiency exists in our society in the RC building. Okay. Okay. Anything you want to discuss? Any doubt so far?